And moving on, we're now going to take a look at two main categories of electricity. Now keep in mind before we begin, there is a whole lot more to electricity than we can cover in a 2-week chapter of an introductory level. My father was a master electrician. It took him 3 to 5 years of studying electricity before he got his license to become a professional electrician. So there's a whole lot more to this than we're going to cover in our class. But we'll get the basics and we'll get them very well starting now. Section 19A, static, and 19B, electric current. Let's begin. And there you see the girl touching her hand to what we call a Van de Graaff generator. Unfortunately, we don't have one here to use. They can be fun, but they can also be dangerous if not used correctly. If you ever get a chance to do this, put your hand on that aluminum ball before turning on the machine. Because if you don't, and turn on first and then try to touch, you'll get a very big shock. And when turning the thing off, hit the off switch first, let the machine completely die down before removing your hand. Now what's happening? Why is her hair standing up? Static electricity is electric charge that is not moving. Well, what happens when she turns on the machine, a conveyor belt made of leather inside starts turning, and it's placed vertically. And the electrons will rub from that leather conveyor belt onto that steel ball, or it may be aluminum, it could be either one. And that aluminum would then send the electrons into her hand, and those electrons would travel throughout her body to the ends of her hair. Now remember, electrons are all negatively charged. So we have an electrostatic force of like charges repelling each other. And once those charges get to the end of her hair, there's nowhere else for them to go. So those charges will now repel each other and make her hair stand up. This can be a very strong force. This force, electrostatic, can be stronger than gravity. Now, in fact, lightning is a big buildup of static electricity, and that force is much stronger than the Earth's force of gravity. But all this happens because electric charges build up, and her hair stands up because all those electrons are the same charge, and like charges repel. Ready? What is electric charge? Electric charge happens when atoms gain or lose electrons. Way back when we did the periodic table in the first and second 9 weeks, we talked about this quite a bit. Atoms that lose electrons become positively charged, and atoms that gain electrons become negatively charged. Think back, we've talked about that quite a bit. So something such as copper would lose an electron and become positively charged. And something such as phosphorus, a nonmetal, would gain those electrons and become negatively charged. Now, I mentioned part of the law of charges on that last page with the girl's hair standing up. The law of charges says that like charges repel, opposite charges attract. Those electrons that went to the end of the girl's hair, those are like charges. They're all negatively charged, so those will repel each other. If we put a positive and a negative together, then those charges will attract. Think of sodium and chlorine from our periodic table chapters. Sodium became positive by giving away an electron, and chlorine became negative by taking on that electron. Those two opposite charges stuck together, attracted to form the ionic bond. Well, even with static electricity, think that way. Like charges repel, opposite charges attract. And it works that way for magnets too, and that's coming up very soon. Ready? There's an electric field. You see the positive and the negative. You see right here the electric field coming out of the positive, going around and back into the negative. And you see that these two are together, and here's why the opposite charges will attract. Because the force comes out of the positive charge and into the negative, you can kind of see they're pulling on each other. Now, if there was another negative, say over here, you can see that this is going to find the nearest negative. So the positive charge will find the closest negative charge and then attract each other. It's kind of like a proton and an electron. Now, remember that also when we talk about magnets, again, very soon. The electric field is the area where we can feel the electrical force. Think of a downed power line. Maybe a storm has knocked down the power line that you see on the sides of roads from the telephone and electrical poles. Never touch those things because they can kill instantly, too much electricity running through them. But if we get even close enough without touching, we may feel that electrical energy leaving that power line, traveling through the air and the ground and into our body. The area where we can feel the electrical force is called the electric field. This has a lot of electrical potential energy that, when used correctly, can be harnessed and used for energy purposes and to give us electricity. Think of batteries that have a positive end and a negative end. That's going to be in the electric current section, but still same idea. The electricity will come out of the positive end, go through the circuit, and back in through the negative end. The battery contains potential energy. Okay, more about that in a little bit later. The field flows from the positive to the negative, so the electrical energy will flow from the positive charges towards the negative charges. That is our electrical field. The electric field is the area where we can feel that electrical force. Ready? Charging with static electricity. Can static electricity be useful? Well, yes. Now, you'll see more details of what you're about to see on here on pages 446 and 447. Friction causes electrons to rub off of one of the fabrics, maybe, and onto another fabric. So think of rubbing a cloth against a balloon or rubbing the balloon against your hair. You've seen that. You may have even done that. And then the balloon might stick to the wall. Well, there have to be other conditions involved. But electrons would rub off from the hair onto the balloon and therefore cause a negative charge on the balloon. That negative charge would attract protons in the wall, and those opposite charges would stick to each other by attraction, and that's how we might be able to get a charged up balloon to stick to the wall. That's just one example. Conduction is when touch charging objects together. So touch a charged object to an uncharged, and some of the electrons will spread to the uncharged and again attract the protons. But these are a couple of ways that we can charge up objects that don't already have a static charge. Use friction by rubbing things together, or conduction by taking a charged up object and touching that object to something uncharged. Another way is called induction. I'll show you this in class, but maybe take some paper bits and sprinkle some little pieces of paper on the desk. Rub a balloon up against your hair, and then put the balloon, don't touch the balloon to the paper bits, but close enough, and if you get a good enough charge on the balloon and in dry conditions, the paper bits may jump up to the balloon. That might work with a plastic comb as well, or even a plastic pen. But remember to do that in a dry atmosphere. If there's a lot of moisture or humidity in the air, which is moisture, then that moisture will interfere with your static experiments. So if you want to do these static experiments, make sure the conditions are dry. And I'll show you these things in class. Ready? Some uses of static electricity. Well, static can be annoying. Wintertime, dry weather, you go to open the car door and get a nice little shock. Can be fun though. You build up that charge by scraping your socks, your feet in your socks against the floor, and then touching your little brother's ear. You can cause him to get a shock. In fact, my son, when he was little, took a piece of string cheese, you know, that shredded cheese you get in the bag at the store, and he scraped his feet against the floor, and he touched the back of my ear, and I never saw him coming, and he shocked me, and he showed me it was a piece of cheese. Well, cheese has calcium, which is a metal, and metals conduct electricity. He was just being a little wise guy, but we learned something, and me being a teacher of this subject, I was able to tell him why. Spray painting, laser jet printing, air filtration, photocopying, all use static electricity, and of course a lot of other stuff as well. But can use static electricity, spray painting, to get really good art. Laser jet printers can use static electricity. Air filtration, we have an air filter in all of the classrooms. You may hear that humming. Static electricity will attract the dust particles and purify and clean the air. Photocopiers and many other things can all use static electricity. Even things in the hospital that might measure the heartbeat. those things may use static electricity and measure electrical impulses in the body. Ready? And those are just a few uses here. I mentioned this just a moment ago. Look at the top right. Now, I'm not a physician. I don't really know exactly what all this means, but right here, this says a normal ECG, electrocardiogram, or electroencephalogram. All right. This is a normal heartbeat. Look, you get a beat, a beat, a beat, and there's a nice normal repetitive pattern. I don't know what the letters are, what they mean, RT, PQ, and S. But look over here, this says small and uncleared P wave indicates atrial fibrillation, an irregular heartbeat. As you see, this goes down. And all this is being measured with a machine that measures the static charge impulses of the heart and the body. This one, you see the line here and the line here, says this person's had a heart attack. And then we get increase in muscle thickness. The heart is too thick, and that can cause some serious problems as well. And I don't know how to read those, but I do know that the machines measure the static impulses of the heart. So some uses of static electricity: muscles and nervous system, heartbeat, and you see on the bottom right picture, I'll tell you about in a moment, the EKG machine measures electrical heart impulses. That's why we get the regular or the irregular patterns on the top picture there. Now, the bottom picture is a smokestack. Now, look here. A few decades ago, people did, and some people still do, that complained about all the pollution that factories would put out because of the smokestacks. Well, not too long ago, fairly recently, maybe a couple of decades ago, people figured out, hey, there's a lot of charged particles in smoke. So let's use oppositely charged plates inside the chimneys or the smokestacks. Now look what happens here. This says, number one, smoke particles pick up a negative charge, so these particles have extra electrons from the waste gases containing the smoke. And as those particles go up the chimney, this says, number two, smoke particles are attracted to the collecting plates. So these have positively charged plates right here in the red. So the negatively charged extra electrons are attracted to the plates that are positively charged, fewer electrons, and by the time the smoke comes out, much, maybe not all, but most of the pollutants have been pulled to the plates. And what comes out is really not smoke much anymore, I'll hit that thing again, but more like water vapor. And water vapor is very beneficial. There may be a little bit of pollutant left in there, but not much. And those plates can be cleaned and reused many times a day. So smokestacks can use static electricity to reduce pollution. Ready? Electric current, this is moving electric charges. The word static actually means not moving. Although when static charge builds up too strongly to stay in one place, then that charge can jump through the air. That's why we do get a shock when we build up charges and then try to open the door. Electrons jump from our body onto the doorknob. Lightning is a great big buildup of static electricity, and when the charge is way too strong, then the charge will jump through the air, either from the cloud to the ground or from the cloud to the ground. It can actually go both ways, and many times the lightning bolts will meet midair. But electric current is moving electric charges through some kind of a closed circuit. We all know, plug things in. Plug in your phone charger, plug in your computer, your laptop, your TV, your Xbox. Without that flow of electricity, those things won't work. Of course, phones have batteries, and so do computers and iPads, but your Xbox probably doesn't. And many things we plug in don't have batteries to use as a backup. The electricity has to constantly go through a circuit and continue to repeat that path in order for things to work. Section 19C will talk about this a little bit more. That's in our next set of notes. Electrons move from high to low concentration. What this means, high concentration is where there are many, many electrons, and low concentration means where there are few. So think of it this way. We're all crowded at one end of the hallway and not allowed to move. And once we're allowed to move, that's like flipping the switch to turn on the lights, connect the pathway, and then we can all move to where there are fewer people, so we'll be more comfortable. and then we can move more easily through the hallway. And that's what electrons will do. They'll gather up, and if the circuit is broken because a switch is opened, well, then they're all just going to sit there. And electrons are a lot more patient than we are. Think of a drawbridge. Once that drawbridge goes down, all the drivers will then continue along the road. Once that switch is closed, we turn on the circuit. Those electrons will then move across the circuit. Where there are many to where there are few. There we have two types. Direct current. Think of a battery. This means, I'm going to draw this one up here. Okay. A direct current means that the electricity will flow like this and like this through the circuit and back and keep on going like this. And there has to be a continuous flow. Think of a battery that has a positive end and a negative end. And the electricity will come out of the positive end, go around into the negative end, and through and through and through and continue. And there's one direction, no backing up. But that's DC. But then you see alternating current here. And electricity may travel like this. And then go through and then like this. So zigzagging as it goes through. There will be a constant change of directions. Not like direct current where it's like running around a track maybe. But this is going to zigzag back and forth as the electricity goes through the circuit. These are things that you plug in. So the wall outlets will give us alternating current and batteries will give us direct current. Ready? Here's a good picture of a direct current circuit. We see the dry cell, which is another name for battery. Keep hitting that darn stand. The current comes out of the positive end, through the switch, through the wire, out of the negative end rather, because the electrons are going to repel, through the switch, through the wire, through the light bulb, and there's a filament up here. The electrons will go in here and light up this filament, which is a wire called tungsten, back through the circuit and continue the path. And there's no backing up and going backwards. It's all one continuous path. That's direct current. Charges flow in one direction throughout the circuit. We have to have a source, and in that picture, the dry cell or the battery is the source. We have to have a path, the conductive wire for the electricity to travel through. Now, not every circuit has a switch, however. Some do, some don't. But the switch is like the drawbridge I mentioned a few moments ago. When we turn off a device, we open this switch. We disconnect the wires on either side of the switch so the electrons cannot cross over empty space. When we turn a device back on, we close that switch and connect those two pieces of wire. So let me show you. Open may be like this. Okay, here's what I'm trying to do. And then switch, close that, and now the electrons can travel through. Okay, probably make fun of my arm like that, but that's okay, as long as you understand what's going on. Okay. Something that's battery powered will use direct current. Okay. Out the negative, as you see here, I may have said that incorrectly a little while ago, but out the negative, through the circuit, through the switch, if there is a switch, there may not be, through whatever the load device is. It's not always a light bulb, it's whatever we're trying to use. And then back into the battery through the positive end, because positive here, electrons are negative, attract, repel, electrons, and continuous. Batteries, though, have chemicals, and the chemicals get used up, then the batteries are dead. Recharge a rechargeable battery, but some aren't, they have to be thrown away. Battery-powered devices, out the negative through the circuit and back in through the positive, and the cycle and the circuit will continue as long as the battery has enough energy. Rechargeable batteries, we can plug those into the wall, store up electric charge in those batteries, and repeat the process. But remember, even rechargeable batteries eventually get to where they won't hold charge and they won't recharge very well anymore. Ready? Oh, forgot about that. Batteries are portable, which allows us to bring our phones anywhere we want to. But batteries are temporary, like we just said. Batteries run out, batteries die out, and even rechargeable ones eventually will become completely dead. Ready? Hey, alternating current. Now you see I was trying to draw this earlier, but this kind of indicates one way, the other way, one way, the other way. And you see the current, both arrows here, we have one way, other way, one way, other way. So electricity and alternating current actually zigzags while traveling through the circuit. Zigzag, zigzag. And this may go one way, this may go the other way. And some of that is sometimes done with electromagnets, and generators will do that. Other times, you plug something in, you get alternating current from the power company, and that's why we're able to use all our TVs and plug-in devices, appliances like refrigerators and stoves and washing machines and so forth. Alternating current has advantages too, which you'll see in a moment, but one of those is alternating current is permanent. As long as the device is plugged in and turned on and there is a source, then we can continuously run whatever device we're running. Alternating current allows charges to flow in both directions through the circuit, and again, a zigzag. These are your plugged-in devices. Now we have to get the electricity from somewhere, not just the wall, but the outlet in the wall has to get electricity from transformers that lead into the buildings and homes, and that comes eventually linking back to the electric company. And a little later on, not now, we'll talk about how that could possibly happen. That's done with magnets and turbines and stuff like that. Now, 60 hertz, remember what a hertz is. A hertz means something happens every second. An oscillation is a back and forth motion. And somebody figured out a long time ago that the oscillation of 60 times per second, I can't do this 60 times every second. That's way too fast. But 60 back and forth motions every second is exactly the right rate for us to have the right amount of electric current. Not too much, not too little. 60 oscillations per second, or 60 hertz, that's what we want. The advantage to alternating current is that alternating current is permanent. As long as we have the device turned on and there's no problem with the circuit, we can watch TV all day, all night, leave the TV on when we go out and come back and that thing is still running. But here's the drawback. The plugs can reach only so far. We might need extension cords. Eventually, though, we have to go beyond the limits of the extension cords. So fixed means not very portable. Okay, how many people are going to carry an 85-inch TV from room to room with them? So there are drawbacks to both alternating and direct current, but there are nice features about alternating and direct. For direct current, the good thing is portability. The negative is needs to be recharged or thrown away and replaced. For alternating current, the nice part is permanent, continuous until we turn off the device, and the drawback is fixed, can't really move around very much. Ready? Now, what is a conductor? Things that allow electricity to pass through easily are called conductors. Remember the periodic table? We said metals give away electrons. Well, electricity is actually electrons moving from one atom to another, and those conductors are made of metals, particularly copper and aluminum. But most metals make very good conductors. Some of them aren't used very much as conductors, but they could be. Think of the wiring in the walls in your home or in the buildings here. Copper. Some are made of aluminum. There may be other metals that are turned into conductive wires. Gold is a fantastic conductor of electricity, and so is silver. But those two are rare and precious and very valuable, which means they're very expensive. In comparison, there's a whole lot more copper in the earth available, so that's why copper in comparison is far less expensive and a lot more commonly used as conductive wires. Our body is also a fantastic conductor of electricity, and so is water. And we've said before, water, even though water is non-metals, water is polarized. The hydrogen end is positive, the oxygen end is negative, like a battery. Therefore, electricity flows through water very well, especially water that's not been distilled. Because tap water, you turn on your faucet to get a glass of water, there are mineral deposits made of metal, calcium especially, in that water that conducts electricity very well. So never mess around with water, because an electricity and water together because that can be a deadly combination. Our body has a lot of metals and a whole lot of water inside. Body and water are both fabulous conductors of electricity. Ready? Well, conductors allow electricity to pass through. What are insulators? These are things that block current. Electric current does not pass through these things. If metals make very good conductors, then what must make a very good insulator? We have nonmetals, such as glass, wood, plastics, and rubber. And these are 4 very common insulators. Electricity doesn't travel through glass very well unless there's far too much electric charge. Wood, plastics, and rubber also stop. That's why even though I have electricity running through the cord to the TV that you're looking at through your computer, the TV and the computer have cords that are wrapped up in plastic and maybe even some rubber inside. That way we can grab the cord and we won't get shocked because of the insulation. And the conductive copper wire inside allows the electricity to go from the outlet into the TV or computer. But insulators are non-metal things that block electric current. Ready? Semiconductor. Now think of metalloids. It's been quite a while since we talked about metalloids. But when we did, we mentioned silicone and germanium as 2 terrific metalloids that make terrific semiconductors. These are small devices that allow some current to pass through a little bit at a time. This is like letting a few people, we've talked about before, a few people go in the lunchroom at a time and everybody else waits in the hall for just a short time. Then the next group of people goes through, everyone else has to wait. And that is so we don't get too crowded. Well, the electrons build up too much in one place, our devices could burn out, catch on fire, and spark. So electronic devices have these semiconductors that will regulate how much electric charge goes through the circuit. Metalloids, remember they're the ones on the staircase on the periodic table. Particularly silicone and germanium make fantastic semiconductors. You will find these things in most every piece of electronics or computer chips, anything to make sure we don't get too much electricity. Most electronics don't need a whole lot of electricity, just a little bit, but the wall outlets supply far too much voltage and current for most of our devices. Therefore, a series of resistors and semiconductors will slow down the flow and allow just the right amount of electric current to pass through. Ready? Almost done. Just a few definitions now. Voltage is the difference in electrical potential or the electrical force. Remember a few minutes ago we said current will flow from high potential to low potential, where there are many electrons to where there are few electrons. And the bigger the difference between many and few, the more forcefully those electrons can move. That's like all of you lined up at one end of the hall, we say go, an empty hallway, and you can all barrel on down the hall at top speed. But if there are people in your way, you're not going to be able to go quite as fast and avoid collisions. Voltage is the force that sends electrons into motion. So when you look at a battery and you see 1.5 volts, that's the amount of force that the battery can push electrons through the circuit. You put 4 of those together, then you have 1.5 times 4 is 6. That's 6 volts of electrical force. That means more voltage. That will also mean more current. So think of voltage as force. We did the laws of motion earlier. And think of current as acceleration and motion. And you can also think of resistance as the mass that resists. So really, voltage, current, and resistance are the electrical equivalents of force, mass, and acceleration. Here's a number, 6.24 times 10 to the 18th electrons. Some guy named Coulomb discovered this number, so we call the unit a Coulomb. A volt is the amount of force needed to move 1 joule of electrical energy for every 6.24 times 10 to the 18th electrons. So a volt is equal to 1 joule of energy for every coulomb of electrons. All right, so 1 volt is equal to 1 joule of energy for every coulomb, which is that number of electrons. And an ampere is how many coulombs travel through the circuit in every second. So this number, let's say you have a 10 amp washing machine, this number times 10, that many electrons move through the washing machine every second. If you have a 20 amp refrigerator maybe, then this number times 20, which is a very large number, that many electrons move through the circuit in 1 second. An ampere is 1 coulomb per second. That is a rate, kind of like a speed. Ready? Oh, resistance. Sometimes, like I've said before, I forget there's another line on the very bottom. A resistance is something that blocks or slows down or hinders the flow of electric current. And the unit we use for resistance is called the ohm, named after a guy whose name was Ohm. Amazing how things in science get their name. Say, voltage is the force, ampere is the current, that's like the acceleration, and resistance is like the mass that slows down the motion, because more mass, less motion, less acceleration. More resistance, less amperage, less electrical motion. More voltage, more force, more motion, more electrical motion. Ready? All right, Ohm's law. I think this is the last page. We have an equation here. Again, think of force equals mass times acceleration. Now, current is the actual acceleration. All right, let me put the other color up here because that'll be easier to see. Current is like acceleration. Voltage is the electrical force, and resistance is like the mass. And you may remember from the laws of motion, A equals F over M, and we write, instead of that, F equals MA simply by multiplying by mass. And this is what we ended up using as Newton's second law of motion. I equals V over R. We use a capital I for current because capital C means Coulomb. V for voltage, a capital V, and a capital R for resistance. So in Ohm's law, all three letters are capitalized. So let's put that up here again. This is acceleration equals force divided by mass. I'm just comparing this new equation to something you're familiar with. These are both the motion, these are both the forces, and these are both the resistances. And remember, we multiply by mass, we get F equals MA. We get F equals MA. So once again, Ohm's law is simply the electricity version of Newton's second law of motion. And we will do practice problems. Here are the units. We measure voltage in a unit called volts. This was named after a guy named Volta. Amperage. We use a capital I for the variable, but a capital A. Really, it's supposed to be a capital A with a little halo above. Can't do that on this computer. So capital A will mean amps. We can also write out the word ampere. And then that's the Greek letter omega. Looks like an upside down horseshoe. Some guy named Ohm came up with this, so we call resistance the ohm. And we're going to do practice papers with this. But again, Ohm's law is like the electricity version of Newton's second law of motion. Ready? And so ends this session. I hope you got a charge out of the lesson. See you next time.